Okay, we are back at problem 6. So hooray! Um, this one was hard. For me, this one was probably harder than even the first one, where I had to learn about the Kardane method or Kardane algorithm. This one was a doozy. I don't know. I saw that this was considered a medium question just because I was stuck at it for so long. And I'm like, this is not. This is. I mean, this was easy. This was ranked as easy. I was like, this is not easy. This is more of a medium. Um. So yeah. Let me read it. So number 6, equilibrium index of an array is an index such that the sum of elements has at lower indices is equal to the sum of elements at higher indices. So write a function that gives the sequence um, R of size n and returns a equilibrium index if any, or -1 or -1 if no equilibrium index exists. So that's kind of a mouthful, but let's just define. Let's make sure that we agree what equilibrium was, because for a long, I mean, half the day was just like, what is equal? What? I thought equilibrium had to be like in. I thought it meant it had to be in the center, because that's what I always thought what it meant in English. But no, it just means that it has to be equal on both sides. Most of the time in reality that happens to be in the center because balance. But no, I'm silly. So it's let me draw out the example that was given in the problem, and maybe that will make it easier to explain in layman's terms what we're trying to find. So I'm going to draw the example array called and A stands for array. A equals, okay. Wow, that's hard. Whoop, 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 whoop. um, 1, 2, 3, 4, 5, 6. So there are 7 elements. 7? Yes. 7 elements total in this array. -7. So this is the example array that I'm doing. 5. What, that was a 1, sorry. This is a 5. 5. Wow. Oof. -4. I think I've gotten better at drawing numbers with my mouse. Zero takes forever. And the output, what we're looking for, like the answer, I'm gonna put O as the output, should be 3 or index 3. So 0, 1, 2, 3. So that is the output. This guy is the output, because 3 is index. Let me just write it in so I won't forget, because that's what confuses. That's what I mean. Really confused me for a long time. I was like, how is it 3? Where did 3 come from? I don't understand. So 3, index 3 is the equilibrium index, because if you add, ooh, what did I do? Oh my god, I just blind everyone watching this video. I'm sorry. Sorry. If you add -7 to 1, it will become -6. And if you add -6 to 5, then it will be -1. And so we're looking for anything at a higher or lower array. So if you so continue from this, if you start with -4 and you add 3, then you get -1, and then you add 0 and still -1. So -1 is equal to -1. So we have 2 as the equilibrium index. See, now that I say it out loud, that sounds so simple to me, but that literally took me like how long to just go, oh, click in my head. It was just like, I just did not get it. And the funny thing is, and this always happens, I was on the toilet and just thinking about it on the toilet, and then it clicked. I was like, oh, and I was very proud. I was like, oh, equilibrium index, got it. It's just, I don't know. It's just, I like nothing has changed except I was just, it just clicked. This is so embarrassing. Okay, so, um, let's see. So we're trying to, basically, we're trying to find the equilibrium of an array. It's a point where it becomes equilibrium both sides. And I was like, what is the real world application of this problem? Because does this happen a lot where we need to find? Anyways, I had a hard time with this with this one, so I'm gonna try my best. I am going to say that I'm going to state the edge cases or the things that we should watch out for. I should code. So we're going to code. We're not going to code, but we're going to pseudocode. I'm actually going to just type it out. So in order to have an equilibrium index, we need an array must be larger than 2. Yeah, because then there would be no equilibrium if there's only two two numbers. Must be larger than 2. So must be larger than 2. And I have to remind myself, if not found, return 1, -1. And there is, I don't know if there's only one, or if there are there multiple E indexes that we should be looking for, or just one. And that, ladies and gentlemen, is why I don't use the mouse to write. Ooh, that's terrible. So the brute force solution would be to use it's, I mean, relatively simple, but it's going to take a long time. The brute force solution is using 2 nested for loops. So brute which equals out to n square. So like a quadratic time, which is not good. So we're just going to declare a left sum and a right sum and start them both at 0. And using the loop, we're going to go through the array and add up all the sums, every single one. And then we're going to use the inner loop, the second one, to determine if any of those numbers happen to equal out to be the same. So in our case, -1 is -1, and eventually we'll find it, and then they'll give us the index. But like I mentioned, it's slow. But you are being more space efficient because you're not establishing any additional data structures. So like we're going to declare left sum and start it at 0, and then right sum and then start it at 0, and then we're going to loop through to get the left sum, to actually get the left sum because they can't stay at 0, to get left sums total for each index. Loop through again to get right sums total for each index. Yeah, and if they find equal sum, or find if left sum and right sum are equal, then return the index as output. And that will give us quadratic time complexity and constant space complexity. That's just kind of that was my original game plan, and I couldn't think of any smarter solution than this. I know there was a better one, but in order to improve the time complexity, we're going to need to do something with the array before we start the actual before. So we need to pre-process it, which means let's see, how do I? Which means it's really similar to this part. It's very similar to the Cadane, which is the first problem that was assigned to us. So we get the total sum of the original array. So is there a way I can move? Oh no, I know what to do. Okay, so this is the sum array. I'm just gonna write it here. Hopefully it's not confusing, but I could explain it. So essentially it's the same. We're just adding up this array. So let's do this. Okay, so the start is -7, and then we moved on to -6, and we're gonna add a 5, and that means it's 1, and then we have, wait, is it negative? No, sorry, -1, and then we're gonna add 2, which becomes yeah, it then becomes 1, and then we're gonna add -4. This kicks it down to -3, and then this is +3, so we get 0, and then we add 0 to 0, which is 0. So we are adding, so this is the sum of every time we iterate through, this becomes a sum, and that's what's down here. Okay. This method is tricky, and I looked it up. Because the only way I could think of was to brute force using a basic double loop. But this one is you need to find the sum of the array, and when you get the total sum of the array, then you just subtract you turn the sum into the working right sum, and then you subtract the right sum one by one, and that's how you could figure out what the right sum. And once right sum is equal to left sum, then you could return the index. And if you don't find it, then you just break out completely and return -1. So let's see. So let's run through this. The sum for this array we know is 0, and the sum for, so you know, if the sum is 0, that means the left sum, and the left sum is -7. That's the starting. That's this one. Then basic math. The right sum has to be 7, because 7 plus -7 is 0. And now we're going to move on to the next one, because we are still iterating through. So how do I find where's the eraser? Okay. Oh, that's not right. Okay. And then we're going to move on. I should probably delete this or erase this. So we started here, and now we're going to move on to -6. So if the sum, well, the sum is still 0, my bad, and left sum is -6, then right is 6. And then we move on to this one, which if the sum is, on the left is -1. How about I erase? This is -1, then obviously it's positive. Okay, so it's pretty self-explanatory. So we get right through and we get these numbers. And oh, hey, look, we found the oh, sorry, I got mixed up by the ones. So if we continue, then we will find our, where's the eraser? So if we continue on our path, then we will find the, so 1 and this -1. And now we found the equilibrium, because this and this will cancel out and equal 0. So we know that this, so we know that 2 is the kind of, well, yeah. So we know from as we iterate through, we will eventually come head to head with -1 on this side and -1 on this side, and the remainder is the remaining index is 2. So let's write this up. I need more space. Maybe I wonder if I can move this. Nope, I can't. Okay. I can't move anything here. Okay, never mind. I'm definitely gonna need more space. So to summarize, we're gonna iterate through the array and get the sum, and then we are going to subtract that one by one to get the right sum, like the right side sum, not like not right side like correct, right as in like on the right. And eventually there will be a point where left sum and right sum will equal both to -1, and at that point we return the index that we are iterating with, like the index that we find that on, and return it. So hopefully that makes sense. So let's start. Let's code this puppy up. Okay. So let's do this one is since I looked it up. So I believe this one is, yeah, this one is very good. This one is the has a time complexity of ONN, but it we had to create a second array called total sum in order to keep the, like, you can see that here because I have the original data here, and then I had to make this up. So that takes extra space, but it's a lot faster. And yeah. Okay, I don't know what I'm doing. Let's see. How do I? No. Okay, I'm gonna erase that because I don't know what happened. Let's start over. And let's get a little bigger. So, what was I doing? Oh yeah, define equilibrium. A, let's just A for array. So we are going to find the sum, total sum. Total sum is now the sum of the array, and the left sum we're going to initialize at 0 as we mentioned before, and then now we're going to iterate 3, 4, 5, num in, you know what, I don't know, for I num in array we are going to total sum. I had to do something with total sum. Yeah, subtract the value of each. And the code is actually really simple. And if the left sum is equal to the total sum, which is our working right sum. Oh my god, I can't I can't talk. I'm like, did I say thumb? Then we're going to return the index. So let me clarify what this means right here is if we happen to be on this iteration or this iteration, yeah, I'm just gonna do this one because it's less messy. This one, then we know everything underneath. I mean underneath. To the left of it is -7, and here to the left is 6. So yeah, or yeah. Oops. Sorry, I had to pause there. My kid woke up. Okay. Okay. And the last thing, return I, and the last thing is left if it doesn't wait, so this should be sorry. Left sum will be added to the array at I so we can start the loop all over again until we eventually return I. And oh, that reminds me. Yeah, I'm just gonna write it out here. Oh my goodness. Yeah, I'm just gonna get the indentation's truly horrible. I really sloppy through this, but we're gonna return if just pretend like this is somehow in line with this. And we're gonna return -1 when because there's none No index found. Yeah. Okay. So yeah. Wait. Oops. Is this off screen? Oh dear. Okay. So yeah. And this is the solution. It's great because we only it's O of n time because we did all these loops at once and we knew that the sum was all we needed at each point to find the left and right until they were equal. The only thing we needed to do was process the array in advance and then save it to a new array that was sorted, and that was that makes it space complexity O and N as well. That's definitely better than the brute force way, but I mean it's a little confusing. It's actually a lot confusing. I had trouble engage. That's why I thought this problem was a medium problem because ah. Anyways, I love a challenge, and this was probably the most challenging one for me, and I really liked it. I thought it was very clever when I saw the tricky solution, the clever solution. That's right, clever. The clever solution. Yes, because it also applied a bit of what I learned from the first solution, the first problem, which is the Cadame algorithm. So that was pretty cool. Anyways, that's it. Bye.